Into the last section of Chapter 4 that we're going to cover, which is Section 4.7, which is over antiderivatives. You know, I really don't even have to use this on graph paper, but I don't think I brought any white paper, so I guess I must do this on graph paper today. Okay, so this is Section 4.7, antiderivatives. Okay, antiderivatives, which is really, and this is Ms. Zachary's words, reverse differentiation. Okay, reverse differentiation. We're kind of reversing. We're putting it in reverse now, okay, going backwards. So really the way we talk about this is how to recover f of x given f prime of x. So if someone gave you the first derivative of a function, how would we back it up to come up with what was the original function? That's what we're doing. We're recovering the original function. So for example, you got to be thinking backwards now. Suppose g prime of x equaled 2x. What would g of x have to equal? X squared, right? Because the derivative of x squared is 2x. So you're reversing. Okay, you're reversing.
What if they depend on that? What if there's a zero? Like, if there's 2x, or there's x squared plus 2 would be...
Oh, right. We're going to talk about that in just a minute. Good question, okay? We're not that far yet, Mr. Mike, right? Okay, suppose our derivative of our function is cosine x. What would be the original function? Sine x. Okay, now when they really discuss, we'll do one more. Suppose your derivative of your function is 2x plus cosine x. What do you suppose the original function would be? There you go, that's right. You just look at it in pieces. Now, the notation, though, when you really get into your textbooks, and this is consistent, is if they gave you g prime of x, instead of saying g of x is the original function, they will always use a capital. It will always be a capital G. When you take the antiderivative, they always use the capitals in the notation. So if your function was f prime of x, this is f of x, capital F of x, coming down. So they always go back with the capital letters. This is just notation. Actually, sometimes they don't put a prime on it. They just say h of x, go back to capital H of x. So when they write this, when they give you a true definition in our textbook, okay, they say a function f, really f of x, is an antiderivative, bless you, is an antiderivative of f if f prime of x equals f of x. Okay, so we need to take these primes off of here to be consistent. I need to get the primes off. The antiderivative of the lower case is the higher case. It's a little confusing, but that's how they use their notation. That's how they're doing the notation. Now, something that was just brought up, which is interesting, is they say, you know, we talked about, well, I don't know, suppose f of x equals x cubed plus 7. Then the first derivative of the function is 3x squared. But what if the function was, instead of x cubed plus 7, what if it was x cubed plus 10? What would the first derivative be? Still 3x squared. So no matter what constant we tuck onto the end of this function, suppose it's pi, the first derivative is 3x squared. So when we're taking antiderivatives, when we're backing this up and we're taking the antiderivative of f prime of x, and we get x cubed, it could be x cubed plus any number. Okay? It could be x cubed plus 100, or whatever, because the constant can just be there. So really, when we're taking the antiderivative, what we're doing is we're having to add a function to it. So then they give in the book on page 231, they change the, well, I hate to say they changed the definition. It's not really the right thing to say. but they alter it. How do I put? They call it. Well, it's a theorem. Okay. Here they say. Well, over here they say. Here's the definition of the antiderivative, and it says a function f is an antiderivative f. Oh, come on, focus, camera. F prime of x equals f of x. I don't know why it's not focusing any better than that. It's supposed to have an automatic focus on it. Sure is coming out blurry. And then over here, it says, but hold on a second. We got some numbers to play with. We got some constants here that we're forgetting. It says if f is the antiderivative, then the most general antiderivative is really it plus a constant. Okay, so we have to include a constant here. Like you can see all those numbers we're losing, where c is the arbitrary constant. And there was a time, it's been a long time ago, where we talked about a family of functions. Note that all of these are x cubed functions. One would be x cubed minus 2, x cubed minus 1, x cubed plus 1, x cubed plus 2. The derivative of all of those functions is just 3x squared. So the derivative of all this family of functions is 3x squared. So we have briefly talked about that, but now when we're taking the antiderivative or we're working backwards, we need to add a constant, add a c to it, as seen here, in order to cover all the bases, in order to cover the family of functions that we could be playing with. So then they come in here and they say, if f is the antiderivative, they make this a theorem, of f, then really we have to write this as f of x plus c, where c is what they call an arbitrary constant. So they changed their, I hate to say they changed their definition, they amend the definition a little bit so that we have to include that constant on there and not just erase it out. Okay, so here's a good question. I'm going to put this, let this be number 6, and we'll let this be part A under number 6. And the question will be, find f of x of, what is the deal with you guys sneezing? Of f of x equaling 3x squared. Okay, what is the antiderivative? But then they tag a little more onto this by saying when f of 1 equals negative 1. And when they tag this additional information of the f of 1 equaling negative 1, this is going to give you information that will allow you to come up with the value of the constant. Okay, you're going to throw a constant on this when you take the antiderivative, and this information will tell you how to get the number value for the constant. So in other words, if f of x is 3x squared, the antiderivative is, anybody know? X cubed plus c, plus a constant, plus an arbitrary constant. Now, we can find the value of the arbitrary constant because they gave us this little information here that f of 1 is negative 1. So this is an ordered pair. X is 1, y is negative 1. So here, if you replace the f of x or the y, the vertical value, with negative 1, and the x with positive 1, you're substituting this ordered pair in to the antiderivative, then it will give you the value of c. So you substitute this ordered pair into the antiderivative to come up with the value of c. So negative 1 equals 1 plus c, or negative 2 is the value of the constant. So then you get the true value of the antiderivative as being x cubed minus 2. So always remember, anytime they give you this extra information, they're giving it to you because they're giving you the method to come up with the value of the constant. If they don't give you the extra information, then it's just x cubed plus c. But often they will tag a little more information on here in order to make it so that you can get the true value of the function. Now here's an example. I'm going to do it real quick and then give you all a break. Suppose they wanted me to get the antiderivative. The original function here is sine of 2x. What is the antiderivative? Now this here is a little harder. Okay, it's a little bit harder. Oh, you know, you can sit here and get a headache. You can figure it out, but it's not really fun. Okay, so what we're going to come up with is, fortunately, we are going to be given some patterns, kind of like we have the patterns or the shortcuts to taking the derivative. We'll have those same shortcuts or patterns to taking the antiderivative, so you don't just have to sit there and rack your brain to try to figure out what in the world must be the antiderivative. So yay, some really smart mathematician has made shortcuts for us. So at this point, I'm going to pause the recording, take a break, and we'll come back and we'll learn how to do these shortcuts. All right, so let's go ahead and keep recording. I'm just starting the continuation of this section, maximize my lovely screen. So we're talking about antiderivatives, and we are fortunate to be given patterns, or what you would call shortcuts or formulas. And so you're going to love these. Antiderivative formulas. Okay, antiderivative formulas. And these are in the textbook on page 232. So if you want to go into your textbook and print this page, if you can you print one page? I don't know if you can or not. Okay, but here's like the first one. It says that if f of x equals x to the n, like x cubed or something, then your antiderivative f of x, capital F of x, is 1 over n plus 1, x to the n plus 1 plus c. Okay, so that's your pattern. And we'll do some examples to kind of reinforce that pattern. And of course, they have to put on here that n cannot be negative 1, because that would make a zero denominator, which is undefined. So you have to have that little stipulation off there to the side. Here's an example which will make that formula more logical. Suppose your f of x is x to the 5th power. Then your antiderivative would be 1 over, increase the exponent by 1, 1 over 5 plus 1, which is 1/6, x to the 6th plus c. So you increase the exponent by 1 over that number, and then x to that power. Okay, so you can see the pattern. Let's do another one. Suppose we have that f of x equals x to the negative 2/3. Okay, you sure don't have to brainstorm this antiderivative. But very simply, your antiderivative is 1 over the negative 2/3 plus 1. Negative 2/3 plus 1 is 1/3, so it's 1 over 1/3, x to the 1/3 power plus c. Because a negative 2/3 plus 1, n plus 1 would be a negative 2/3 plus 1 is a third, and then the negative 2/3 plus 1 is the new exponent. So this becomes 3x to the 1/3 power plus c. And you could check it. What if you took the derivative of this? If you took the derivative, it'd be 1/3 times 3, which is 1, x to the 1/3 minus 1, which is negative 2/3. 1x to the negative 2/3. So you can take the derivative and reverse the direction, woo, and check your answers very carefully. Okay, so here's a second formula. Okay, if f of x equals sine of kx, like sine of 2x or 7x or a third x or something times x, then your antiderivative will be negative. The antiderivative of sine is a negative cosine. It will be a negative 1 over k cosine of kx plus c, because the derivative of a negative cosine is a positive sign. Okay, so here's an example. Suppose you're asked to find the antiderivative of sine of 3x. K is 3. So your antiderivative will be a negative cosine, but it will be a negative 1 over 3 cosine of 3x plus your constant. By the pattern, K is 3, so it will be a negative 1 over 3 cosine 3x plus c. Okay, very simple, nothing difficult here, but you've got to learn these patterns. Okay, here's another one. And this is nothing big. But if you have a constant in front of your function, like 4x cubed or something, then your antiderivative is keep the constant and take the and then take the antiderivative of the function. So you just kind of maintain the constant. Okay, you maintain the constant. Even if it's a -1, you just hang on to the -1 and take the antiderivative of what is beside it. So for example, if you have that f of x equals 2 sine of 3x, well, the 2 is going to just stay with the antiderivative. So the 2 is like the k, it just stays there. The antiderivative of sine 3x is a -1/3 cosine 3x plus c. So you can see this is identical to the example above, other than having the k value of 2 in the original function. So this becomes a -2/3 cosine of 3x plus c. So if there's a constant there, carry it through to the antiderivative. We could do another simple one like that. Suppose your original function is 3 cosine of 1/2 x. What is the antiderivative of cosine, you think? Positive sign, right? The derivative of sine is positive cosine. Okay, so it's positive. So it's 3, but you got to have the k, which is going to be 1. It was going to be the 1/2 sine of 1/2 x plus c. So it's 3/2 sine 1/2 x plus c. Okay, so you kind of generated that one yourself, but up here on number 2, you can put on here, if you had a cosine function, then your antiderivative is the positive sign, is 1 over k positive sine kx plus c. Okay, so there's your sine and your cosine. I guess we could put these in boxes or something. I don't know. These are your standards. And so there's your big ones. Here's some more of them, which I think that you can probably generate yourself. But if f of x equaled secant squared kx, what do you think the antiderivative is of secant squared? It's tangent. So this is 1 over k tangent kx plus c.
On that last one, the 3 cosine 1/2 x, shouldn't, when you pulled it out and made it 1 over k,
No, not with the, with the trig functions, you're right. I'm sorry. It should be 1 over. I am sorry. 1 over a half. I'm rusty myself, which makes this a 6. Thank you. Sorry about that. Thank you for watching me close. I'm really running a little bit rough this morning. Change that and make that a big 6. 3 times 1 over 1/2 is 3 times 2, which is 6. Sorry about that. Okay, see if y'all can remember this one. These are the ones that even I can't seem to keep straight. If it's cosecant squared kx, what is the antiderivative of cosecant squared? That's the cotan, but it's the negative cotan. So this is -1 over k cotan kx plus c. Okay, so these are really some more of the standard formulas. Number 6, again, these are really the standard formulas still with all your trig functions. If you have that your f of x is secant x tan x, or secant kx tan kx, that's a secant kx tan kx, then your antiderivative is secant x, or in this case 1 over k secant kx plus c. So these are really just your formulas now. And then one more. If your function, or like your derivative of your function, is cosecant cotan, cosecant kx, cotan kx, then your antiderivative is a negative 1 over k cosecant kx plus c. So you're reversing all of your derivatives. Okay, so now we have them all. So now let's do some more examples. Additional examples. Okay, take the antiderivative. Suppose your function is x cubed minus 1 over x to the fourth. They want you to find the antiderivative. So this is going to kind of mix up all of your formulas. Well, before I would find the antiderivative, I would write this as x to the negative 4. That second one, or that fraction, make it an x to the negative 4. So now you're taking the antiderivative, which is a capital F of x. Okay, the antiderivative of x cubed is going to be 1 over the 4 plus 1, which is 1/4 x to the fourth power. That's the antiderivative of the x cubed, minus the antiderivative of x to the negative 4 is 1 over negative 4 plus 1, which is negative 3, x to the negative 3, plus your arbitrary constant. So this is 1/4 x to the fourth plus 1 over 3x cubed plus c. There's your antiderivative. You'll get pretty good at this. You just have to be very careful you don't mix them up. You start checking your answers, then you start getting the procedures a little bit confused. And it's hard to not check your answers by taking the derivative. Okay, suppose you take your function of sine pi x minus 3 sine 3x. You're supposed to take the antiderivative of this. Okay, well in this case, pi is your coefficient of x, like your k. So the antiderivative of sine x is a negative 1 over k, or 1 over pi, cosine x, minus the antiderivative of 3 sine 3x is 3 times 1 over 3 cosine of 3x. Let me get this here. The derivative of cosine is sine, so this is supposed to be subtraction of a negative number, right? So we got to get a negative in here. Where do y'all want to put the negative? This is this subtraction, and then the negative, I'll put the negative in front of the 1/3. How's that? So this is a negative 1 over pi cosine of x plus cosine, oops, I forgot to put the plus c. Plus c. All right, suppose we have f of x, this is where I get it messed up, equals secant x tan x. What is the antiderivative? Just secant x. There you go. These are the ones that I'm a little bit weak on. So what if your original function is 4 secant 3x tan 3x. Hang on to the 4. One over k, right? So it's 1/3 secant x, right? Plus c. Now, here's where this gets interesting, and I'm just going to do this very quickly. Really, this is 4/3 secant x plus 4c, right? But c is any arbitrary constant, so whether you multiply it by a number or not, it's still c. Now, sometimes if you want to be technically correct, but you're not going to see this, you could call it like c sub 1 and c sub 2, c sub 3, but they're all just an arbitrary constant c. Yes, back in the back, Yes, why am I so messed up?
Yeah, and up top.
What am I thinking? Did I do it more than once?
Number 2, there should be pi x, not cosine x.
Yep, you're right. Sorry. Man, I am so off. Not crisp today at all. It's because it's been a long time since I've done it myself. Okay, now there is a new notation that you're going to see a lot in the future, and I didn't even write it here. This should be a capital F of x. Okay, so now we have a new notation. This is part D. When we take the antiderivative, it's called integrating. So, and this is what it looks like an elongated S. Okay, so instead of them having to take the antiderivative of the given function, they can just put this integral sign. Okay, this integral sign. This is called, the f of x dx is referred to as the integrand, and this little symbol here, this elongated x, is the integral. And the verb is to integrate. Okay, the verb is to integrate. Do the following integration. So, if you're integrating like 2x cubed plus 4x minus 1, this would almost be written something like f of x plus g of x plus h of x dx. Okay, so if you're integrating like this, when you're through integrating, this would be capital F of x, if you wanted to say plus c1, plus capital gx plus c2, plus capital hx plus c3, but we collect them all into one arbitrary constant. Okay, we collect it all into one arbitrary constant. And we don't normally do this, but really this should have a square bracket. It's not h of x dx, it's f of x plus g of x plus h of x dx, collectively with one dx on the end. Okay, so here's what it'll look like. Suppose they ask you to integrate 1 over x squared minus x squared minus 1/3 dx. We don't normally put parentheses around all that, but it's terribly tempting for me to put parentheses. Yeah, they are putting parentheses, are they? They kind of do at times. Sometimes they do and sometimes they don't. It's not consistent, but you could put parentheses here because all of that with 1 dx, okay? So before you want to jump into this, I would rewrite this as x to the negative 2. Okay, so this becomes 1 over negative 2 plus 1 minus 1 over 2 plus 1 What do you think the integral of 1/3 is? 1/3 x. We've not done that one, but the integral of a constant is the constant times x. So this becomes, this is an interesting looking answer now, -1 over x minus 1/3 x cubed minus 1/3 x plus c. So they can give you a bunch of questions without ever saying, determine the antiderivative of the following. They just say integrate. They don't have to say anything. They just give you the symbol. Right? Suppose we want to integrate something that looks like this. 4 plus the square root of x over x cubed dx. Okay, now we don't have any special rules for these quotients, so you would want to rewrite this as 4x to the negative 3 plus the square root of x over x cubed. I guess I'm going to have to do that. Okay, so this is 4x to the negative 3 plus what? And then a negative 5/2. This would be a 1/2 on the top minus a 6/2 on the bottom, right? A 1/2 minus a 6/2 is a negative 5/2. Okay, so this becomes 4 over negative 3 plus 1 is a negative 2. And 1 over a negative 5/2 plus 1 is a negative 5/2 plus 2/2, which is a negative 3/2. So this is a negative 2x to the negative 2 power minus 2/3 x to the negative 3/2 power so this is a negative 2 over x squared minus 2 over 3x to the 3/2 plus c. So it's just step by step. It's not hard, but boy, there were a lot of steps there. Okay, suppose we want to integrate sine of 2x minus, this is a cosecant, that's an S, CSC, cosecant squared x dx. Now, I've not done this, but you could do this. I'm just going to write it so you can see the notation. This could be rewritten as sine 2x dx minus, that's a cosecant squared x dx. You can split this up, kind of like the f of x plus the g of x plus the h of x. You can split it up if you want to, and that's what you're doing. You're integrating the first one, then you're integrating the second one. But if you are to write it like this, you need to put the dx with each integral. Okay, what's the antiderivative of sine 2x? If I can get this right, okay. It's 1/2 cosine 2x, negative, right? Minus, the antiderivative of cosecant squared x is cotan x, but it's going to have to be a negative cotan x plus c. So this turns out to be a negative 1/2 cosine 2x plus cotan x plus c. question? All right, now, is this E, is this right? Yeah. Okay. Solve the initial value problem. This is how they'll ask the question. Solve the initial value problem. And this is how they give it. dy dx equals 9x squared minus 4x plus 5, and y of negative 1 equals 0. So in other words, when it's an initial value problem, they're going to give you this extra information that will give you the ability to come up with the value of the arbitrary constant c. Okay? So when you take dy dx is like y prime, right? So you take the antiderivative and get y. This is going to be 9/3 x cubed minus 4/2 x squared plus 5x plus c. Which is simply 3x cubed minus 4x squared plus 5x plus c. Oh. Okay, now you're going to solve for c by using this given information, which is the ordered pair negative 1, 0. So replace the y with 0 and the x's with negative 1s. Which will then give you the value for c. So replace the y with 0 and the x with negative 1. So do y'all get c equaling 10? Okay, so now the true function, original function, is 3x squared, no, 3x cubed minus 2x squared plus 5x plus 10. So initial value problems is they're going to give you initial values such that you can determine the value for c. Okay, suppose we have dv dt equals 8t plus cosecant squared t, and my initial value is that v of pi halves equals a negative 7. So you're going to take the antiderivative, which is the same thing as integrating, and then you're going to use the initial value to come up with the arbitrary constant. So v is going to equal 8 halves t squared. Increase the exponent by 1 and divide by that number. The antiderivative of cosecant squared is a negative cotan t. My cotans look funny. I'm trying so hard to write this. I think the S's just need to be a little bit sharper. Okay. So now we have this initial value, which is the ordered pair pi halves negative 7. So replace the v with the negative 7 and replace the t's with pi halves. This is interesting. Okay, what is cotan of pi halves? Tangent of pi halves is undefined, right? Is undefined. So cotan is 0, right? So this is 0. This is weird. And this is wrong. This is not 8 pi squared over 4. What is it? 2 squared is 4 and 4 times 2 is 8, right? 2 squared is 4 and 4 times 2 is 8. So this is a negative 7 equaling pi squared plus c. So negative pi squared minus 7 equals c. So this result is really weird looking, but it is 4t squared minus cotan t minus pi squared minus 7. My cotans just look bad. My cosecants are bad. I had to try so hard to write it so you can read what I've written. Now this is an interesting situation. This is hard for me to even write. This is the second derivative of r with respect to t. And it equals t2 over t cubed. Then it says, this is all unusual notation, dr dt evaluated at t equaling 1 is 1. And then it says, these are all your initial values, parameters here, r of 1 equals 1. There's all your information. So this is like your second derivative. This is your first derivative being evaluated at 1. And this is your original function. See all that? Okay. So my first antiderivative will be dr dt. And I have to rewrite this. I can't do it with it written as like that. It's 2t to the negative 3. So this is 1 over negative 3 plus 1. No, I may have done that funny. That's what it is. Okay. So it ends up equaling what? A negative 1 over t squared? Now, we can come up with the value for c, because according to this given information, when dr dt equals 1 when t is 1. So it's kind of like the ordered pair 1, 1. So this says that 1 equals negative 1 over 1 squared plus c, or c equals 2. So now we know that dr dt equals negative 1 over t squared plus 2. Now, we get r. r is the antiderivative of that, so I've got to write it again as a negative exponent for me to be able to do this. So now, this is negative. 1 over negative 2 plus 1 is negative 1. And here, if you want to call this c sub 1 so you don't confuse all your c's, you can. I don't know, that might make it worse. So we have r equaling positive, right? 1 over t. R is just 1 over t, and it's positive, plus 2t plus c sub 1. Now we were given, I wish they would have done something other than all these 1s, okay? We're given kind of the ordered pair of 1, 1 in order to come up with this value of this constant sub 1. So this is going to say 1 equals 1 over 1 plus 2 times 1 plus c sub 1. So we have 1 equals 1 plus 2 plus c sub 1. 1 equals 3 plus c sub 1, or negative 2 is c sub 1. So the grand answer is that r equals 1 over t plus 2t minus 2. Because they gave me so much initial value information. Okay, we're almost done. I know you are getting tired. Okay, we're almost done. I'm moving pretty slowly because my mind is not working very quickly today. Okay, antiderivatives and motion. Antiderivatives and motion. Okay. How in the world do I show you this? Okay. You have your position function, s of t. When you take the derivative of the position function, what do you get? You get velocity. When you take the derivative of velocity, what do you get? Acceleration. Okay. So the first derivative is velocity, the second derivative is acceleration. So now, if you do it backwards, your antiderivative of acceleration is velocity. Your antiderivative of velocity is your position function. Okay, so you reverse it. You take the derivative of acceleration, you're going to get velocity. You take you integrate acceleration, you get velocity. You integrate velocity, you get your original function. Just reverse it. Okay, you just reverse it. And when you start doing these, remember that gravitational pull is that right? Gravitate. I went a little wild. Gravity. Great. I got a little carried away here. Okay. Gravity is a negative 32 feet per second squared, or a negative 9.8 meters per second squared. I think I really got carried away with the IONs and the A's. A little bit wild here, making up my own word. Like extracalifragilistic expialidocious. You ever seen that written? I was getting a little carried away. That's kind of... Okay, so I'm going to read example 5 from the textbook on page 233. And we will go after this. I know you are just really... I think it's because I'm going too slow or something here. Okay, this is on the bottom of the page. A balloon, a hot air balloon, ascending at a rate of 12 feet per second. Now that's not acceleration, right? It's not feet per second squared, it's feet per second. So it's a constant velocity increase going up at a constant velocity. Is at a height of 80 feet above the ground when it drops a package. How long does it take the package to reach the ground? Stupid question. Okay. Here's a balloon. Oh, I don't do this well. With the basket or whatever.
We had an identical problem with this in physics.
Whatever. Oh, really?
Yeah, and like 90% of the people in the class couldn't get it because they all thought, oh, that took way too long to get to the ground. I have to redo it. They always did it over and over again, but the right answer was like a lot longer than most people thought was realistic.
Well, I'm not very good at this kind of stuff. Okay, the velocity is 12 feet per second, and the initial height, initial values are always h sub zeros, okay? Something sub zero. You're 80 feet off the ground. So really, your initial velocity when you drop the package, okay, you were originally going up at 12 feet per second, and your original height was at 80 feet. Now, the package is falling at a gravitational pull or acceleration of a negative 30, we're in feet per second, so a negative 32 feet per second squared. That's your original acceleration when you let go of the package, and it gets kind of constant at that acceleration, okay? So now, if we want velocity, we're going to integrate acceleration. So if I integrate this negative 32, and this is dt, I don't know how to tell you that, but it is dt, okay? When you integrate this, so when you, this is so hard, this is not hard to say, but it's hard to get it all written down. Your velocity is to integrate acceleration, which is going to be a negative 32t plus c. This is your velocity, a negative 32t plus c. Now what in the world is c? If this is your velocity function, I can just tell you very quickly, your constant is going to be your initial velocity. If it was your position function, your constant is your initial position. Okay, the constant will always be the initial information at that moment. But what we know really is that at time equaling 0, the velocity was 12. So we can go through the whole algebraic process to prove this, because we got the velocity is a negative 32t plus c. But if your velocity was 12 at a time of 0, then sure enough, your c is 12, which is your initial velocity. So when you integrate acceleration and get velocity plus c, the c is really going to be initial velocity. So now you have that your velocity function is a negative 32t plus 12. So what is our position function? Well, your position function, which is s, is to integrate velocity. Well, to integrate velocity, you're integrating a negative 32t plus 12. So your position function is a negative 32 halves, which is what, 16, right? Is a negative 16t squared plus 12t. I've got to get off the book. That's bending. Plus another constant. Now, what was our initial position? 80 feet. This is going to be 80, but to prove this to you, at time equaling 0, your initial height was 80. So if you put this in here, you get 80 equaling a negative 16 times 0 plus 12 times 0 plus your constant. So sure enough, 80 should be the value of the constant, which is your initial position. So your position function is a negative 16t squared plus 12t plus 80. So here's your position function, which is really your height. Here's your velocity. And here's your acceleration. Okay, there's the three. Now, I don't even know what the question was. Oh dear. The question said, a hot air balloon is ascending at a rate of 12 feet per second and is a height of 80 feet above the ground when a package is dropped. How long does it take the package to hit the ground? What does that mean? Time when height equals 0. So, time when height equals 0 time when height equals 0 is your position function. 0 equals a negative 16 t squared plus 12t plus 80. Solve this sucker for t. So 0 equals a negative 4 times 4t squared minus 3t minus 20. Does this thing factor? No. Now what? T equals a negative b plus minus the square root of b squared minus 4ac all over 2a, right? Where a is 4, B is a negative 3, and C is a negative 20. So your time is a negative B, which is a negative of a negative 3, plus minus the square root of a negative 3 squared minus 4 times A times C all over 2 times A. Now we're taking the A to be 4, the B to be negative 3, and the C to be a negative 20. You're just looking at the quadratic, the second degree trinomial there. Okay, so therefore you have T equaling 3 plus minus the square root of 9 plus 16 times 20, which is 320. Is that right? Over 8. Did I do that right? A negative times a negative makes a positive. Subtracting a negative number. So if you do the positive version of the radical, what do you get? I think that if you put the negative version, that's a negative number, right? Big time. This isn't going to work. So what do y'all get here? Less than 3 seconds? Is that what y'all get? .64 seconds for that package to hit the ground. Okay. Y'all got all that? You feel smart?
I hope so.
Okay. I tell you what I'll do on this test. I will give you the, not the sine and the cosine or the tangent, but the cotan, the cosecant, and the, what am I missing? Secant. Okay. Those three, I'll put those derivatives and antiderivatives on the board for you on this test. I'll write them. But you need to know the sine, the tangent. No, you need to know the sine, the cosine, and the tangent. But I will do the reciprocal functions on the board for you, okay? So just get those first three. Study hard. That review is there online. No, it's got to be some free response. And don't forget the quiz. If you want to get half credit back, fix number 4.